A single dollar bill can survive being folded over 4,000 times. Yet it's not made of paper at all. A coin looks solid and simple, but it's struck with enough force to flatten a car. And the ink on a $100 bill can shift color right before your eyes, somehow without a single drop of dye. That level of precision shouldn't be possible for something printed by the billions. So how do mints and printing bureaus turn cotton, metal, and specialty ink into currency trusted by millions of people every single day? Let's step inside and find out. Most people call it paper money. It isn't. If a dollar bill were made of real wood pulp paper, it would disintegrate the first time it went through a wash cycle. Instead, it's built from a fabric. And that one substitution is the reason it can survive being crumpled, soaked, and stuffed into pockets for years. It starts as raw cotton and linen fibers, blended at a ratio of roughly 75 to 25. These fibers arrive at the paper mill as loose bales, almost like the raw material for a t-shirt rather than a notebook. Unlike ordinary paper, which is made from wood pulp broken down by chemicals, currency stock is built from long textile fibers, which is exactly why it can bend thousands of times without tearing along a crease the way a page from a notebook would. The fibers are cooked down into a slurry, then pressed into massive rolls of blank currency stock. No printing yet, just a tough, cloth-like sheet that crinkles differently than anything sold in an office supply store. Even at this raw stage, the sheet already contains the security features that will matter later. Colored fibers scattered invisibly through the pulp, and a security thread fed directly into the slurry before the sheet ever dries. Once the blank stock arrives at the printing facility, it goes through a sequence that hasn't changed much in over a century, even though the machines running it are now computer-controlled to a fraction of a millimeter. First comes offset printing, which lays down the background colors and fine guilloche patterns, those looping, wave-like lines that are almost impossible to replicate by hand. Next is intaglio printing, the step that gives currency its raised texture. Engraved steel plates are packed with ink and pressed into the sheet under thousands of pounds of pressure, forcing ink up out of tiny grooves so it sits slightly above the surface. Run a fingertip across a real bill, and that texture is intaglio ink, standing proud of the page. After that, sheets pass through letterpress, printing for the serial numbers, and treasury seal, each bill receiving a unique numeric fingerprint, so no two are identical. Then comes overprinting for security threads and watermarks, some of which are embedded directly into the fiber during the paper-making stage, long before ink ever touches the sheet. Finally, massive guillotine cutters slice the printed sheets, often 32 or more bills per sheet, down into individual notes, and high-speed counting machines stack them into bundles of 100, moving faster than the human eye can track. Here's the part that sounds impossible. The green ink on the back of a bill isn't a single fixed color. Certain denominations use ink that shifts from copper to green depending on the angle you view it from, a property borrowed from the same chemistry used in some car paints. It's not a printed illusion. The ink itself physically bends light differently depending on viewing angle, and no ordinary desktop printer can reproduce that effect. From loose cotton fibers to a finished bill takes weeks, not hours. Much of that time spent drying, curing, and inspecting under UV light for defects. Any sheet with a single misaligned digit or ink smear is destroyed before it ever reaches a bank. A coin looks like the simple option. It isn't. A coin seems like the low-tech cousin of paper currency. Just stamped metal, right? In reality, striking a single coin requires more raw mechanical force per square inch than almost any other object most people touch in daily life. Coins begin as enormous coils of metal, usually a copper core clad in a nickel alloy for something like a quarter, though the exact blend changes by denomination and country. These coils look more like something from a steel mill than a mint, arriving as tightly wound rolls of sheet metal weighing thousands of pounds each. Before any of that metal reaches the mint, it's tested for exact composition. A coin's weight and electromagnetic signature have to match a strict specification because vending machines, coin counters, and banks all rely on that signature to sort real currency from fakes. A coil that's even slightly off in its copper to nickel ratio gets rejected before it's allowed anywhere near the press. The coil feeds into a blanking press, a machine that punches out thousands of blank metal discs per minute. the way a cookie cutter stamps shapes from dough. Except this dough is solid metal moving at high speed. What's left behind, the metal webbing between punched holes, gets recycled and melted down for future coils. The blank discs then move to annealing, where they're heated to soften the metal, making it pliable enough to take a detailed design without cracking. After a cooling and washing cycle to strip away oxidation, the blanks pass through an upsetting mill, which raises a slight rim around the edge of each disc. That rim isn't decorative, it's what allows coins to stack neatly and protects the design from wearing down through handling. Now comes the striking press, the most dramatic step in the entire process. A blank disc is fed between two engraved dies, and the press slams them together with somewhere in the range of 35 to 60 tons of force in a fraction of a second. That single strike embosses both faces of the coin simultaneously, pushing metal into every groove of the die to form the portrait, lettering, and rim detail all at once. That 60-ton strike happens roughly 700 times a minute on a modern coin press. To put that in perspective, it's roughly the same force used in industrial metal stamping for automotive parts. Except here it's being repeated with pinpoint accuracy on an object smaller than a bottle cap, over and over, without the die ever being allowed to drift out of alignment by more than a few microns. Finished coins are counted, bagged, and sealed by weight rather than by hand count. A single bag might represent tens of thousands of coins, verified by scale rather than a person counting one by one. But none of this, the fiber, the ink, the tonnage, matters if a coin or a bill can be faked. So how do you stop a counterfeiter with a good printer? Somewhere inside nearly every modern banknote is a feature invisible under normal light, one that only reveals itself when a specific wavelength hits it. It's not a gimmick. It's the last line of defense against forgery. These features begin not on the printing floor, but in a chemistry lab, where security ink and embedded threads are engineered years before a single note is printed. Fluorescent fibers, magnetic particles, and color-shifting pigments are all developed in tightly controlled substances, some available only to government mints, never sold commercially. New security features can take years to move from lab to circulation, since every candidate ink or thread has to be tested against the latest generation of scanners, copiers, and printers on the market. Engineers essentially have to out-design technology that doesn't exist yet, building in a margin of protection for tools that will only become more capable over the life of a printed note. The security thread is embedded directly into the paper stock during manufacturing, not printed on top later, meaning it's physically woven into the fibers of the note itself, visible as a thin vertical line when held up to light, running from top to bottom rather than sitting flat on the surface the way ink would. Under ultraviolet light, that same thread often glows a distinct color depending on the denomination, something a standard color copier has no way of reproducing because copiers don't emit UV light in the first place. Watermarks are created using variable paper thickness pressed into the fibers while the stock is still wet, so the image only becomes visible when light passes through. Another feature that's essentially impossible to fake with ink because it isn't ink at all. It's a physical variation in material density. Then there's microprinting, text so small it looks like a solid line to the naked eye, but reveals full readable words under magnification. Because it's printed using engraved plates rather than a digital file, most consumer printers simply can't resolve detail that fine. Modern security cameras and vending machines can verify a bill's authenticity in under a second by scanning for a dozen of these features simultaneously. Magnetic ink patterns, UV response, thread placement, and precise size. A level of instant verification most people walking past a cash register never think twice about. By the time a note reaches a bank vault, it's already passed automated inspection for every one of these features, with any note failing even one check pulled and destroyed before it circulates. That's how a bill goes from raw cotton fiber to something that can survive a washing machine, how a coin goes from a flat metal coil to a design struck with tens of tons of force, and how invisible ink and woven thread quietly stop counterfeiters before a fake bill ever reaches your wallet. None of it happens by accident, and almost none of it is visible in the moment you hand over a bill or drop a coin into a vending machine. It's precision, chemistry, and engineering most of us never think about until now.